Good day, students. Welcome back. Lesson 8, Video C, correlation. Okay, this is the video where we will talk about the theory as to how do we calculate the correlation. And what it is, it's a number. In the last video, we talked about the strength. Does the relationship between two variables look strong or moderate? We'd like to put a number to it. And so this video is all about calculating that number. I'll say right off the bat, StatCrunch will be doing the calculating, but we've got to have the theory in our heads as to why this is the right number. All right, calculating this correlation coefficient. Step 1, if the association is linear, so you've got to look at a scatter plot and look for a linear relationship. The next step is to quantify the strength and direction by calculating the correlation. The letter that we'll use, of course, is R. I don't know why, of course. Correlation coefficient starts with C and C, but R is the right letter here, so that's the symbol for correlation. And to understand this number R, what we first have to realize is that the units of measurement do not matter. So if I have some data, and I'll just switch to the example here. Example, I've got 370 automobiles and the two variables. X is going to be the weight. So how heavy is the automobile? And based on the weight, we'll put that on X, we'd like to predict the fuel efficiency. And we'll measure that in miles per gallon. So over here on the left, I've got pounds versus miles per gallon. This is USA. Right, this is how we measure things over here in America. We'll use pounds for the weight. We'll use miles per gallon for the fuel efficiency. If I take these same cars and transport them across the Atlantic Ocean over to Europe, over in Europe, they won't measure things in pounds, they'll use kilograms. So we're changing the units. Okay, the X variable changes in units. And instead of miles per gallon, they'll probably use something like kilometers per liter. So we're changing the units in X and Y. And what I want you to notice is that the picture looks pretty much the same, right? You can see the pattern. You can see there's a relationship. I'll say this is pretty darn linear. You could argue there's a slight curve here, but I think if you're seeing that curve, you might be looking too hard for a curve. So we'll say this is linear. Whatever the strength is over here on the USA side, however I measure that strength, it has to be the same measurement over here. Okay, it's the same cars, and if I change the units of measurement, my measure of strength and direction cannot change. So the only comment I'll make here is that whatever the heck R is, R has to be the same. Okay, so units don't matter, however I'm measuring my X and Y variable. That being said, we're going to do a little review. We learned about z-scores back in lesson 5, possibly 4. I can't remember with these chapter titles yet because this is all brand new, but we did learn about z-scores regardless. So when we calculate correlation, the trick is this. We will be converting everything to z-scores. When we convert to a z-score, the units go away. No longer will I be working in kilograms or pounds. I'll transform it to a z-score. Okay, so get this erased. Let me flip the slide. And, well, that can stay for a second. In both cases, the correlation coefficient is, I calculated this at home, R is negative 0.868. Now don't worry about where the heck that number came from. There's no way with the information we have that we could get that. But the correlation, a measure of strength and direction, is the same for USA as for Europe. It'd be the same exact number. Okay. One more bullet point. Another way that we can change the units is to take our data values, and here's the trick, convert to z-scores. So just think about this for a second. There's 370 cars here. I have 370 X values. I have 370 Y values. That means I would have to convert 370 numbers to a z-score and 370 more numbers to a z-score. By hand, this is a pain. We won't really do this by hand, but we have to understand the ideas. All right, enough with the cars. Let's go back to the main example. And the main example is direct loans. We're using for a certain college how many loans did they grant, and based on loans we will predict the loan value, how much dollar value in loans a school granted. So let's remember on the next page, how do we calculate a z-score? Z equals, remember what we do, we take our data value, we subtract off the mean, and we divide by a standard deviation. In this unit with regression, we're working with two variables, so we'll actually have to calculate z-scores for both the x and both the y variables. Okay, if I flip the slide, nope, we'll leave it down here. So I'll change this to symbols. I could calculate a z-score for x. I'll put a little subscript x here, and this would turn out to be x minus the mean for x. So what symbol should I use here? I'll put x with a bar over it. We're probably familiar with y bar for the mean for a y variable, so this will be x minus x bar, and we'll divide by the standard deviation of x. Okay, so this is for one variable out of our two. We'll do the same exact thing for the y variable. So I would convert z, I'll put a subscript y, equals my y value, subtract off the mean for y, which is y bar, and divide by a standard deviation, subscript y, for the y variable. Okay? For large data sets, this will take you forever. We do not want to do this by hand. But the ideas are what's important in this video. I'll flip, you've got the data in the note packet plus the summary statistics. Just let's think about doing this by hand, even though that we won't. For the direct loans example, we had 63 schools, the two variables. Loan value was y, number of loans was x. On average, schools granted 2,308 loans with a standard deviation of this 2787. Okay, on average, schools granted in dollar values just a hair under $5 million on average, with a standard deviation of about 6.7 million. Here's the data set. This would go down 63 rows. Here's what we would do. We would, number of loans is the x value there. And I have this column of z-scores. You can see it in your note packet. I did it automatically. We really won't ever do this in class. But I would have to convert every single school number of loans to a z-score. And I would have to convert every single school, loan values, to another z-score. And based on these z-scores now for each school, this is how we would calculate the correlation. We would look at the relationship between these z-scores. All right? Big pain. Let's look at a picture and see what's going to happen. All right, so it says below on the next slide, we'll get there in just a second, we've created scatter plot for direct loans. But be careful, look at the axes. It's not number of loans anymore on x. It's now the z-scores. And it's not loan value on y, it's now the z-scores. And you can see, just get my page right, compare this picture to the previous picture with the original values. It looks exactly the same. Okay, so we've converted to z-scores here. What I'd like to remind you of, let's put a line right here at 0, straight on down. On the horizontal axis, these are the z-scores for x. And if I said to you, hey student, what's the mean for a z-score? The answer is always 0. That line there is at the mean for the x z-scores. So up at the top, I can just label this. I can put, this is the mean z-score for x. It's right at 0. We should do it again. I can do it for y. Down here is 0, straight across. Put this on your graph in your notes. That's at 0 in the y direction. This is the mean z-score for the y variable. If you remember back to algebra class, sometimes when we have a coordinate set here on the graph, we can number these quadrants. I'll do the same exact thing. This top right is quadrant 1. Top left, quadrant 2. Down here is quadrant 3. I'm just going to stick it here in the corner so I've got a little room to write. And then that'll be quadrant 4. So this is quadrant 4. Let's keep the goal in mind. We're trying to calculate the correlation. I would like to measure the strength and direction of this relationship. I'd like to do that with one number. That number is the correlation coefficient. We have a very strong, very positive relationship. Where are most of the points falling on this graph? Easy question, right? Which two quadrants? Almost all the points are up here in the first quadrant, and then the rest of them are all down here in quadrant 3. Maybe 1 or 2 down here in 4, depending on what side of the line these are falling on. Maybe a few up here in quadrant 2. But with a very strong, very positive relationship, almost all the points are in those first and third quadrants. All right, let's pick a point. I always pick this one just because there's lots of room to write. I could pick any point here in the first quadrant. What the heck is the z-score for this point in the x direction? Well, this point's above average because it's above 0. So this has a positive z-score. It's a number bigger than 0. So this point here, the z-score for x is positive. I'll put like a plus sign in parentheses. So the z-score for x here is positive. What's the z-score for y? Well, here's the mean for y. It's at 0. And I'm above average. I'm above that line 0. So the z-score for y is also positive. All those points up in quadrant 1 will have positive z-scores for x and positive z-scores for y. And what happens if I multiply z-scores? If I take a positive times a positive, the result is positive, right? So, let's put a little line here. If I multiply z for the x times the z for the y, put a little dot there for multiply if that helps, the answer will clearly be a positive number. I could do that for all those points. This would be a positive product of the z-scores, positive, positive, all of them. And with a very strong positive relationship, I have quite a bit of these positive points. All right, down to the bottom corner, quadrant 3. Pick your favorite point. I don't know, here, this one. Doesn't matter which one you circle. What the heck? Let's look at those z-scores. What the heck would the z-score for x be? I'm now below average. I'm to the left of 0. So for this point, the z-score for x is negative. I'm below average, left of 0. What's the z-score for y? Am I above average or below? I'm below. That means that the z-score for y is also negative. What happens if I multiply negative times negative? Negative times negative is positive. So, I got to put an arrow here, painting myself into a corner. If I took z for x and multiplied times z for y, I would get a negative number for all those points down here in the third quadrant. Calculate correlation. I convert to z-scores. Thank you. Positive. I calculate correlation. Step 1, we convert to z-scores. Step 2, for each pair, now I start multiplying these z-scores together. Imagine doing this by hand. We're lucky to be taking stats where we have software to do this for us. All right. Overwhelmingly, the points are in quadrants 1 and 3. some things to consider. I do have a point, I'll put it in a box here. Getting all over the place, but I need space to write. That point there is in quadrant 2. Even though I'm going to write up here. That point is in quadrant 2. There's a few of those with our very strong positive relationship. What's the z-score for x? The z-score for x is negative because I'm to the left of 0. But the z-score for y is positive because I'm above average in y. When I multiply a positive times a negative, I'll get a negative. So we're going to have a few negative products, not too many, but just a few. So quadrant 2, the z for x is actually negative. The z for y is positive. And if I multiply those, z for x times z for y would be a negative number. All right. So it's a lot to think about, but here's all we're going to do. For every dot, every pair of data, or every ordered pair of data, do the z-scores, multiply them together. In this case, we get a lot of positives, just a few negatives, and all we're going to do is average it out. That's how the correlation is calculated. The idea makes sense. When I'm very strong and positive, I will have an overwhelming number of positives averaged out with a few negatives, right? What happens as this relationship gets weaker? The points are going to start doing this. As the points start doing this, I'll still have a lot of positives in these two quadrants, but as the points go this way, we start to get more data in these two other quadrants. Some positives offset with a few negatives now. That number will not be as overwhelmingly positive, okay? And as the points become just perfectly scattered here, like a blizzard of points, I'll have about an equal number in all four quadrants. If that's the case, we'll have about an equal number of positives averaged out with about an equal number of negatives. And if I average lots of positives, lots of negatives, I'll get to 0. So with no relationship, no linear relationship, that correlation will turn to 0. The reverse could happen. As the points start to form a negative relationship, we'll get more points in these two quadrants until it becomes super strong, where we're in the opposite case of here. Almost all the points are in quadrants 2 and 3, and when I average out those products, it will be overwhelmingly negative. So it's a lot to think about, but that's the idea. The good news for us, StatCrunch, we'll click the button, we'll get the number. All right. My soapbox spiel is over. Let's get through these notes. For direct loans, we clearly have a positive association with a very strong positive relationship. Most of the points are in the first and third quadrants, right? First, we labeled with that Roman numeral 1, and third we labeled with that Roman numeral 3. So they're almost all here and here. Take a point in the first quadrant, multiply the z-scores, and the result is z for x times z for y equals positive times positive equals a positive number. That's all those points up there. First quadrant. Third quadrant. Down here in the bottom left corner. Take a point in the third. Multiply the z-scores together. Z for x, again, times z for y. These are the negative times negatives. Result is positive. It's easy once we just repeat it 100 times on one video, right? We have a few points in the second and fourth quadrants. Here and here, those z-scores turn out to be negative. Z for x times z for y will be a negative number. I'll write it out like this time. It could be reversed. one of the two z-scores will be positive and the other will be negative, and the order doesn't matter. Either way, those will multiply to be a negative number. Other things to think about. Remember, we're measuring the strength. How strong is that relationship? For points further from the origin, so think about these schools way up here, the product is going to get big, right? The product of the z-scores will get larger. Think about this. This line is at 0. This line is at 0. What happens when I take numbers very close to 0 and multiply those together? So like a 0.3 times a 0.6. You'll get a number very close to 0. These numbers close to the origin actually have very little impact on the correlation coefficient. It's the ones out here that will really inflate the correlation and make it a large positive. This z-score is bigger than 3 times another number bigger than 3. Multiply together, you're going to be 9 point something, 10 point something. So these outliers will really control the correlation, and these will have very little impact. For points close to the origin, the product of the z-scores will get close to 0. It's super important when we're working with correlations to check those scatter plots. If you have one outlier in there, it can throw the whole thing off. So you want to investigate that point, make sure it's not a typo or an error, and that it really does belong in that data set. Okay, moment of truth. Trying to set the record for the longest video here of the whole semester. We want a single number that quantifies strength and direction of a linear association. The correlation adds up all those z-score products and averages them out. In quotes, it's not a true average. The number does the job, and hopefully you can see why it does the job. Here comes the formula. Remember that the symbol is R, and R equals. It's like an average, so we'll have a big divide sign here. Remember, that's the summation symbol, so I'm going to add up, I'll put parentheses for clarity, z for x times z for y. So convert to z-scores, multiply together, add them up. Now I'll average them out. I have to even check because I rarely use this formula. Okay, it's n minus 1. Just notate what this is. This is add up products of the z-scores. And this is the, quote, average them out part. You will rarely use this formula, but you've got to understand the idea. It's so easy to get the number on StatCrunch, but we'd like you to understand what's going on. All right, so if you flip the page, you can see, now you might think a statistics instructor goes home and can't wait to calculate correlations by hand, but it's not the case. Can't wait to get home and calculate them using StatCrunch. Number of loans versus loan value. The number, here's R, was a 0.983189. Very strong positive relationship. Can you think what this number might max out at? I mean, it seems awfully close to 1, right? So I'll give you a hint from the next video. The biggest a correlation can get is positive 1. So we're very close to a perfectly positive relationship. It says to interpret this value. The variables, so what are the variables? X equals number of loans, and Y equals that loan value have a very strong positive, very strong from the number, positive from the number, because this is positive, linear relationship. Where did linear come from? Here's a subtle but important point. Linear does not come from this number. Linear came from our eyeballs. We looked at a scatter plot. We saw that it was linear. Okay, so this comes from the scatter plot. Very strong positive is verified, and here's the number, 0.9839, blah, blah, blah. All right, so as if you haven't had enough yet, I thought we would quickly look at a negative relationship. So I pulled the hurricane data. In the hurricane data sets, the two variables, we're using the maximum wind because that's easy to measure for meteorologists. To get a maximum wind measurement is easy, and we're trying to predict the pressure. To get a pressure reading of a hurricane is not as easy. In fact, from the year 2010, there was actually a couple of hurricanes with no measurements. But we can get the wind. Okay? Discuss the idea behind that correlation of negative 0.937. All right, so we don't want to leave you hanging. Here's the negative picture. As wind goes up in a hurricane, pressure tends to decrease. So you've heard as the pressure is dropping, that means it's a stronger storm. I calculated off to the side X bar. The mean max wind was 72.14 miles per hour. Y bar. That's the mean pressure was 979.94. I don't even know what the units are. I'm going to guess millibars, but who knows? I think that's right. And let's put those, like we did last time, we have not converted to z-scores, but we could. Let me put a line at 72.14, which would go right about here. And so somewhere there is X bar at 72.14. The mean pressure was 979.94, right at 980 here. Okay, so here's a line at Y bar. Clearly, this is negative. R was equal to negative 0 point something, 937. If I label the quadrants 1 and 2, 3 and 4, I'm going to put the marker down so you know we're almost done here. With this very strong negative relationship, where are the points falling? It's the opposite case of direct loans, right? Almost all the points are up in quadrant 2 and down in quadrant 4. I've got 1, maybe 2 that are in quadrant 1. The z-score products would be negative. The z-score products would be negative. I'll average those out with 1, 2, possibly 3 positive numbers. When I average out a bunch of negatives plus a few positives, the result is overwhelmingly negative. And how overwhelmingly negative? Well, this is a very strong negative correlation, right? Negative 0.937. The biggest this could get is negative 1. So this is awfully strong, and that means that if I know the wind pressure, I can fairly accurately, or excuse me, if I know the maximum wind speed, I can fairly accurately predict the pressure of a hurricane, right? We're going to be using X to predict Y, and with this, we feel good about it. All right, it could have been the record, I'm not sure, but thanks for watching. We'll see you in class.